Let's go ahead and start recording. Okay, so this right here is, again, the remaining portion. We're talking about UV vis spectroscopy, if you remember. So the absorption of the UV vis photon is going to cause an electron transition. This is going to happen between a lower energy molecular orbital. If you had an atom, it would be atomic orbital, to a higher energy molecular orbital. So remember when we talked about HOMO and LUMO? And for anybody that didn't have me last semester, maybe the last person you had would have talked about HOMO and LUMO, hopefully. If not, it's also in general chemistry. Okay? So Gen Chem 1 also has the concept of HOMO-LUMO. So HOMO is highest occupied molecular orbital, right? And so right here we see this is the highest energy orbital that is occupied with electrons. Can everybody see that? Okay. See in the red? Okay, so when you have orbitals, atomic orbitals combine to give you molecular orbitals. The atomic orbitals are going to go in. They'll give you the exact same number of molecular orbitals because energy is neither created nor destroyed, right? And so if we had a carbon and hydrogen, they would both donate an orbital. That would give you then 2 molecular orbitals, and that would give you a pattern of bonding and anti-bonding orbitals. So these right here, when we're looking, are going to be our bonding and anti-bonding orbitals. Okay, so we fill in electrons, 2 per orbital, right? You can't have more than 2 electrons per orbital. If they're degenerate, you'd fill them in 1 at a time, right? And then you double them up. Okay, in this case, we have no degenerate ones, just to simplify this issue. Okay. Okay, so we've filled them up. They are filled up to the highest occupied molecular orbital. The next one up is the lowest unoccupied molecular orbital. Is everybody okay with that so far? Okay. So when you input energy into these systems, what you're doing is you're going to boost up these electrons, say if you input visible light or UV light. Okay? So it's going to boost up an electron. This is this blue orbital right here, going from this one right here up to this LUMO right here. Can everybody see that okay? And that's going to correspond to a frequency. That frequency is one of the frequencies of light that compound absorbs. All right. This would then be another one between the HOMO and the LUMO. Notice that's a pretty short band. And so that would have low energy, low frequency. Okay. Or long wavelength, right? Okay. And so this one right here would be going from the HOMO up to another one that's past the LUMO. See, that's higher than the LUMO. It does not have to be between the HOMO and LUMO. It can be higher energy orbitals. Those would be higher energy light, photons. That would be higher frequency or lower wavelength, right? So this might be blue or green, okay? This one here would be something like red. Is that making sense to everybody? Did I lose anybody? Okay, fantastic. Okay, so again, this one right here, the longest wavelength max, is always going to correspond to the HOMO to the LUMO, because that's going to be your smallest possible gap that you could jump. Okay? Any other jump is going to be a larger gap. Can everybody see that? Okay. Yeah, so that's always your lowest energy transition. It's always your wavelength max. That's going to be the highest wavelength because that's your lowest energy. Okay, so let's go ahead and look at this conjugation. And this is your HOMO-LUMO transitions. So if we look at this right here, these are 2 alkanes. What we notice is we have a filled sigma, which is your bonding sigma, and then we have a empty sigma, which is anti-bonding sigma. Okay? Now, the sigma, does anybody remember what sigma is? Single bonds, yeah. These are the type of bonds that are single bonds, right? And so these are the molecular orbitals that form your single bonds. This would be your anti-bonding molecular orbitals. If you remember what this looks like, it basically just has an exact opposite of where you would have the electrons between the 2 atoms, right? And so it directly just pulls them apart. They typically are your lowest and highest energy. This is why the sigma bonds typically don't react as fast and don't take place in a lot of the reactions. And then your anti-bonding sigmas are going to be extremely high energy. That's why you almost never see them.
Can you explain how it's the lowest and highest energy? Is that what you said?
Yes. So the bonding one is where it's directly in between, and that's the most stable, right? Versus above and below, which would be your pi bonds. Okay? Does that make sense that that's the lowest energy, most stable? Okay. And then these would actually be on the exact opposite sides. So these would be, instead of between, exactly opposite. And so that would actually be pulling your electrons from between and having them only on one side. And so it's a lot less stable, right? Because you're completely ignoring the other one. Okay? That makes sense? Okay. Okay?
And so the UV light jumps one of the electrons into the luma? Is that?
Okay, so this is always your smallest gap, your wavelength max. That's your lowest energy difference,
Right.
or highest wavelength difference. Okay? And that's because, by definition, HOMO has to be highest,
Yeah.
LUMO has to be lowest, right? And so by definition, those always have to be your closest ones.
Okay.
Yeah.
So that's where it would.
So if you only have all sigma bonds, then that gap is a sigma gap. Yeah. So you're only ever going to have, if you have sigma bonds only, you have no pi bonds, then that gap's actually going to be very large. Okay? As compared to these other ones. That making sense? Okay. Okay, so keep in mind pi bonds are above and below, right? And so they're not directly shared between the two atoms, and so they're less stable that way, aren't they? But also, when you're not having them being shared when they are anti-bonding, they're also not as unstable. Because again, they're above and below. Okay? They're not directly opposite. So think of sigma anti-bonding as you're literally like, no, 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 you don't get this with your little brother or something, right? Okay? And you're holding it away from that other atom. Okay? And then this would be more like this, where you're like, nah, don't do that. And so you're holding it to the side. Which one could it, like the other one, reach and grab? Holding it to the side, right? And so this is lower energy when you're talking about that anti-bonding orbitals for your pi anti-bonding orbitals. Because again, it's holding it to the side, right? Not opposite. Okay. And so your energy difference between a HOMO and LUMO, which is again your shortest frequency, shortest energy, longest wavelength, right, is going to be smaller. And we can see this demonstrated with this figure. Everybody okay with that? Okay. Fantastic. All right, so what happens when you conjugate? Well, this is actually going to break these up even more. And so these molecular orbitals are always the average of your atomic orbitals. Okay? And so what ends up happening as you conjugate, you're actually going to get shorter and shorter gaps. These are going to correspond to higher and higher wavelengths, right? Okay. Okay. And so this is actually that behavior of conjugation. Remember when we talked about conjugation, it shifts them about 40 wavelength nanometers. That's actually what we're seeing, is we're seeing the shortening of this gap here. Okay, so let's talk about the transition that occurs in formaldehyde. Upon absorption of UV vis, the photon's not a pi to pi anti-bonding, like you might expect. Instead, it's going to be the non-bonding pi orbital. This is going to be called an N to pi star. These stars, by the way, are high energy. That's what they denote. Okay, they denote an excited state, meaning high energy states. Okay, and so that's actually what this is communicating to you. So it's an N to pi star. This is because the HOMO in this case is not actually down here. This is a bonding orbital, right? It is instead on the average line, which is a non-bonding orbital. Okay, so let's go ahead and cover this again because I'm seeing some confused faces. Okay, so these right here that are below, this is the energy right here. That would be just the average energy of your atomic orbitals. Okay? Anything that's on this line is the same energy as it just being in the individual atoms. So it has no energy either way, prompting it to either make an molecule or break a molecule. Okay? It's just not energetically favorable either way. Same energy as the individual atoms. Okay, so the stuff down here, these are bonding orbitals, right? And bonding orbitals mean that they're lower energy than the individual atoms would be, and so they prompt making bonds, right? Okay. So they're energetically favorable to make these. So putting electrons in these is energetically favorable, right? These right here are the anti-bonding orbitals. They're the higher energy than having them on the individual atoms. Okay? And so these ones right here, putting electrons in these actually separates the two atoms. It causes them to not want to make molecules, not bond, right? Okay, everybody okay with that part right there? Okay. Okay, so if you have a HOMO that is a bonding orbital going up to an anti-bonding orbital, that's going to be higher energy, right? If you then have a HOMO that is actually a non-bonding orbital, that's actually going to be a lower energy transition. Okay? And that's actually what we see here with this carbonyl. Can anybody tell me why that would be? Number of electrons, right? So when you fill these orbitals in, they're filled in by the valence electrons, right? And oxygen has more valence electrons. So it's going to cause you to have to fill in further up, and that's going to cause a difference in that transition, right? Okay. And so that's actually the carbonyl's fault, the oxygen specifically's fault. Even though it's a double bond, it's very similar to this, right? Also, keep in mind that you have this oxygen here. This oxygen right here doesn't have more hydrogens, does it? No. And so it doesn't have the orbitals from those hydrogens combining in. Okay. Okay. Let's go ahead and go on to the next chapter. We'll do some NMR.